Welcome to APCV 320 Computational Thinking and Doing. Today we will talk about theory of computation. Lecture slides were adopted from Professor Henry Wirshan, Applied Computing and Computer Science Program Director, who taught this class during the fall semester of 2020. We will be covering theory of computation from Brookshire and Brylow book, Computer Science, an Overview, Chapter 12. We will first study questions regarding what computers can and cannot do. Then, we will see how Turing machines are used to identify the boundary between problems that are solvable by machines and the problems that are not. Particularly, we will identify the halting problem, whose solution falls beyond the powers of algorithmic systems and therefore beyond the capabilities of today's as well as tomorrow's computers. Moreover, we will find that even among the machine solvable problems, there are problems that do not have any solutions from any practical point of view. Finally, we will examine complexity of problems which lead us to a public key encryption system. So our goal in this presentation is to investigate how capable computers could be. We want to understand what machines can and cannot do and what features are required for machines in order to employ their full potential powers. In the previous learning topics, we have seen many examples of Python functions. On this slide, we begin with the more general concept of computing mathematical functions. A function in its mathematical sense maps a collection of possible input values to a collection of output values. By applying a function, we can map an input to a single output. An example we studied is the sort function that sorts out a list of input values into an output list that has same entries as those on the input list but are arranged in the order of increasing value. There are other function examples, such as the factorial function, whose inputs are integer values and whose outputs are values representing the calculated factorial results. Among the computable functions, we want to be able to classify them. The process of determining the particular output value by a function that is given an input is called computing the function. The ability to compute the function is important because it's by means of computing functions that we are able to solve problems. For example, to sort a list of numeric values, we must compute the sort function on a given list of elements. Thus, a fundamental task to address is to find techniques for computing functions that lie beneath the problems we want to solve. Some functions can be computed easily. For example, a function to convert measures in yards into meters is simple to compute. Some functions, however, are very complicated. As we consider functions with increasing complexity, we are forced to apply more powerful techniques for computing them. Naturally, we may have a question whether we can always find a system for computing functions regardless of their complexity, and the answer is no. In mathematics, there are functions that are so complex that there is no well-defined step-by-step process to compute them. In turn, such functions cannot be computed by an algorithm. They are called non-computable functions. We will have an example later for a non-computable function, the halting problem. In contrast, the functions whose output values can be determined algorithmically from their input values are called computable. For decision problems that are computed by functions that output only 1 or 0, the universe of the possible problems fall into decidable functions which can be computed by algorithms for possible input values, and undecidable functions which have no algorithm that can be constructed to output a correct answer. The distinction between computable and non-computable functions is important. Note that machines can only perform tasks described by algorithms. If we discover that the solution to a problem requires the computation of a non-computable function, we can conclude that the solution to that problem lies beyond the capabilities of machines. On the other hand, if the problem solution is computable, it's possible to build machines to compute the computable function that's powerful to approach the problem. Turing machine was proposed by Alan Turing in 1936, which is used as a tool to study the capabilities and limits of machines today. A Turing machine's computation consists of a sequence of steps that are executed by the machine's control unit. Each step consists of observing the symbol in the current tape cell, writing a symbol in that cell, possibly moving the read-write head one cell to the left or right, and then changing states. The symbols are viewed by the read-write head during execution. The exact action to be performed by a Turing machine is determined by a program, which tells the control unit what to do based on the machine's state and the contents of the current tape cell. It's the conjecture that Turing machines have the capability of solving any algorithmically solvable problem. Church-Turing thesis states that the functions that are computable by a Turing machine are exactly the functions that can be computed by any algorithmic means. As of today, Church-Turing thesis is widely accepted. That is, the computable functions and the Turing computable functions are considered the same. The significance of this thesis is that it gives insight to the capabilities and limitations of computing machinery. More precisely, it establishes the capabilities of Turing machines as a standard to which the powers of other computational systems can be compared. Based on the thesis, if a computational system is capable of computing all the Turing computable functions, it's considered to be as powerful as any computational system can be. Based on the previous Turing Church thesis, we define a universal programming language. A universal programming language is a language with which a solution to any computable function can be expressed. Most popular programming languages are examples of the universal programming language. For a universal programming language, if a programmer finds that a problem cannot be solved using this language, the reason will not be a fault of the language. Instead, it will be that there is no algorithm for solving the problem. You might find it surprising that a universal language need not to be complex. Indeed, the bare bones language is quite simple. We will call it bare bones because it isolates the minimal set of requirements of a universal programming language. Let us now consider the procedural statements in bare bones. There are 3 assignment statements and 1 control structure representing a loop. Following Python-inspired syntax, we adopt the policy of writing only 1 statement per line and use indentation to mark the body of a loop structure. Each of the 3 assignment statements requests that the contents of the variable identified in the statement be modified. The first allows us to associate the value 0 with a variable. The other assignment statements are essentially opposites of each other, i.e., increment and decrement. As a closing example, the instruction sequence in figure 12.4 results in the product of the values associated with x and y being assigned to z, although it has the side effect of destroying any non-zero value that might have been associated with x. The while structure controlled by the variable w has the effect of restoring the original value of y. In this manner, the movement of today to yesterday can be accomplished by the sequence shown in figure 12.5. Thus, although bare bones itself does not have an explicit copy instructions, we often write programs as though it did, with the understanding that to convert such informal programs into real bare bones programs, we must replace the copy statements with their equivalent while structures using an auxiliary variable whose name does not clash with a name already used elsewhere in the program. Let us consider what would happen if we did this in the case of this simple program. While x not 0, increment x. We want to know what would happen if we started this program with x assigned the integer value representing the program itself, as shown in figure 12.6. In this case, the answer is readily apparent. Because x would have a non-zero value, the program would become caught in the loop and never terminate. This slide shows the halting problem. Informally, the halting problem tries to predict in advance whether a program will terminate or halt if it started under certain conditions. If we call the example function with the argument x being 1, the loop will not be executed and the program's execution will quickly terminate. However, if we execute the program with any other value of x, such as 0, the loop of the function will be executed forever, leading to a non-terminating process. In this case, then it's easy to conclude that the program's execution will halt only when it is started with x assigned the value 1. However, as we move to more complex examples, the task of predicting a program's behavior becomes more complicated. In fact, in some cases, the task is impossible. The test book shows a proof to indicate that solving the halting problem lies beyond the capabilities of machines. The proof applies a technique, a proof by contradiction. The proof is based on a statement for the halting problem in a precise manner. Particularly, it is stated as the problem of determining whether programs in a minimum universal programming language called bare bones are or are not self-terminating. The proof concludes that there is no algorithm for answering this question in general. That is, there is no single algorithm that, when given any bare bones program, is capable of determining whether that program is or is not self-terminating. If you are interested in digging more about this problem as well as the proof, you may reference the problem statement as well as the proof within a formal context. In summary, we can say that the halting function is not computable, and because the solution to the halting problem relies on the computation of that function, such problems are called unsolvable problems. So we investigated the solvability of problems, including the unsolvable problems. Starting with this slide, we are interested in examining whether a solvable problem has a practical solution. We will find that some problems that are theoretically solvable are so complex that they are unsolvable from a practical point of view. By studying complexity of problems, our goal is to develop a classification system that tells us which problems are more complex than others, and ultimately which problems are so complex that their solutions lie beyond practicality. For example, there have algorithms existed to hack passwords in a login system. Yes, the solutions typically take too long time to find the correct password from the search space. Investigating the complexity of a problem is ultimately concerned with the time it takes a machine to execute a solution to the problem. Note that this is not measured with the size of the program representing the solution. If there are solutions to resolve a problem, the time complexity of a problem is defined to be the time complexity of its best solution. Unfortunately, finding the best solution to a problem and knowing that it's the best is often a difficult problem in itself. To mitigate this problem, we can use big theta and big O notations to classify problems. When we were addressing the algorithms topic earlier, we use big theta, big O notations to classify algorithms according to the time required to execute them. For example, the insertion sort algorithm is in the class big theta and square. The sequential search algorithm is big theta n, and the binary search algorithm is in big theta log n. Big theta is able to present the complexity more accurately for a program than big O. If a problem is in O and the square, it means it has a solution in O and the square, but it may have a better, more optimal solution. For example, a sorting problem could be solved by an insertion sort that is big theta and the square, but the problem also has a better sorting algorithm, merge sorting, that is big theta and log n. Our investigation of sorting algorithm tells us that the problem of searching within a list length n elements that are sorted is in O I log n, because the binary search algorithm solves the problem. Moreover, researchers have shown that the searching problem is actually in O log n, so the binary search represents an optimal solution for that problem. In contrast, we know that the problem of sorting a list of length n is known to be in O n log n. Thus, the sorting problem is a more complex problem than the search problem. Note that time complexity is a primary concern we have when investigating the complexity of a problem. There is another alternative to measure the complexity in terms of time. The alternative is to measure storage space requirements, which results in a measure known as space complexity. Space complexity measures a problem by the amount of storage space required to solve the problem. Now let us classify our problems, polynomial versus non-polynomial problems. We say that a problem is a polynomial problem if the problem is in O f of n, where the expression f of n is either a polynomial itself or bounded by a polynomial. The collection of all polynomial problems is represented by P. Note that our previous investigations tell us that the problem of searching a list which is in big theta of log n and the problem of sorting a list which is in big theta of n log of n belong to P based on their complexities. In addition to class P, there is another collection that represents all the problems that can be solved by a non-deterministic algorithm in polynomial time. What is a non-deterministic algorithm? It is an algorithm that has steps that may not be uniquely and completely determined by the process state. Why identify P and N of P and NP problems? Identifying the problems that belong to P is closely related to questions regarding whether problems have practical solutions. Indeed, the problems that are outside the class P are characterized as having extremely long execution times, even for inputs of moderate size. Consider, for example, a problem whose solution requires 2 to the power of n steps of an algorithm which is considered less efficient. An algorithm whose complexity is identified by an exponential expression is said to require exponential time. The fact that the problems that are theoretically solvable but are not in P have such enormous time complexities leads us to conclude that these problems are essentially unsolvable from a practical point of view. Computer scientists call these problems intractable. In turn, the class P has come to represent an important boundary that distinguishes intractable problems from those that might have practical solutions. Thus, an understanding of the class P has become an important pursuit within computer science. If a problem is difficult to be solved, it's certainly a bad thing, right? The truth is, in some cases, a difficult problem could become an asset rather than a liability. Here is a problem of our interest. The problem of finding the factors of a given integer doesn't have an efficient solution that can solve it. This means for a number involved that has its representation requiring several hundred digits, the task to find its factors would be interactable, even if modern technology were applied using the best factoring techniques currently known. The failure to find an efficient way of determining the factors of large integers has been applied to produce a popular method of encrypting and decrypting messages in the field of cryptography. The method is known as the RSA algorithm. It's a means of encrypting messages using one set of values known as the encrypting keys and decrypting those messages using another set of values known as the decrypting keys. People who know the encrypting keys can encrypt messages, but they cannot decrypt messages. The only person who can decrypt messages is the one holding the decrypting keys. That means the encrypting keys can be widely distributed without violating the security of the system. Such cryptography systems are called public key encryption systems, a term that reflects the fact that the keys used to encrypt messages can be public knowledge without degrading the system's security. Indeed, the encrypting keys are often called the public keys, whereas the decrypting keys are called the private keys. So this slide demonstrates an example and the math behind the encryption algorithm. To choose the values, we need to pick two distinct prime numbers, P and Q, and the product of the two values will result in another value which will be used for encryption-decryption. Next, we are going to choose another two values, E and D. E is for encryption and D is for decryption. So E times D must be equal to K times, open parenthesis, P minus 1, close parenthesis, times, open parenthesis, Q minus 1, close parenthesis, and plus 1. K is another value involved here, and it is held to an integer. So in summary, as long as the conditions are satisfied among the amount of values and P, Q, and E and D values are chosen for encryption. So let us use an example to demonstrate the math behind the method. So we have two prime numbers to learn, P equals 7 and Q equals 13. And then we get N, which is the product of the two prime numbers, and N equals 91. So after that, we have E, which is for the encryption, and D is for the decryption. And E and D are chosen because if we apply multiplication between the two numbers and we get 145, which equals to 144 plus 1, and 144 is equal to this sub-expression, and this sub-expression is composed of key P minus 1 and the Q minus 1, and with this sub-expression, we also see that K's value is determined as 2. So based on the calculation here, and we have the encrypting keys include N and E, and the decrypting keys include N and D. So to use the RSA method, first we pick two distinct prime numbers P and Q, whose product is N. Then we pick two other positive integers E and D such that E times D equals K times P minus 1 times P minus 1 plus 1 for some positive integer K. Thus we have selected 5 values P, Q, N, E, and D. The values E and N are the encrypting keys. The values D and N are the decrypting keys. The values P and Q are only used for constructing the encryption system. How to encrypt a message that has the binary digit form as 10111 in binary notation, which is 23 in decimal notation for some positive integer K. We are calling these values E and D because they will be part of the encryption and decryption process respectively. Thus, we have selected 5 values P, Q, N, E, and D. The values E and N are the encryption keys. The values D and N are the decrypting keys. The values P and Q are only used for constructing the encryption system. So 100 is the encrypted version of 10111. So the message is received by the receiver. So how does the receiver decrypt the message using the private keys? This slide presents the calculation used to encrypt and decrypt the message. Now we have the private keys and D and N as one of the public keys we use to encrypt the message. The encrypted message we received is 100. At first, we transform this into a decimal number, which is 4. Then we apply a power operation. This time, the exponent, which is the D value, is one of the private key values for this decryption. D is applied as an exponent. The power operations value is this larger number. After that, we apply division operation. The operation to the second operand to use is one of the private keys. It's 91, so this value is used here. Now, after this division, we get a remainder. Okay, the remainder is 23, and the 23 is transformed back into the binary notation, and the bit pattern is 10111, which is exactly the message, the original message encrypted from the beginning. So the decrypt message at the receiver party is A10111, and that means we are able to decrypt the message correctly and based on the private keys. In summary, an RSA public key encryption system is generated by selecting two prime integers P and Q, from which the values N, E, and D are generated. The values N and E are used to encrypt messages and are therefore the public keys. The values N and D are used to decrypt messages and are the private keys, as shown in figure 12.14. The beauty of the system is that knowing how to encrypt messages does not allow one to decrypt messages. Thus, the encrypting keys N and E can be widely distributed. If your adversaries were to obtain these keys, they would still not be able to decrypt the messages they intercept. Only a person who knows the private keys can decrypt messages. The security of this system is based on the assumption that knowing the encrypting keys N and E does not allow one to compute the decrypting keys N and D. Is it possible to create algorithms to compute the decrypting keys? Indeed, there are algorithms to do that. One approach could be to factor the value N to discover the values P and D whose product produces N. Then the algorithm can determine the decrypting key D based on P, Q, and E. The algorithm, however, takes years to resolve the keys if P and Q are large. Thus, the content of an encrypted message could remain secure long enough. So this week's lecture was short, and I encourage you to read through Chapter 12, Theory of Computation from Brookshire and Brylow book. If you have any questions, please feel free to email me. And in Module 11, we will discuss the final project, which requires Python programming.